NASA is preparing a new aircraft reconnaissance campaign for the winter of 2026 and 2027, built specifically to fly directly into something atmospheric scientists have suspected exists for over a decade, but have never actually measured up close. It's called a jet superposition, a rare configuration where the polar jet stream and the subtropical jet stream, two separate high-altitude windows. Currents that normally sit at different heights and different latitudes stack directly on top of each other in the same airspace. Researchers have linked this exact configuration to some of the most violent tornado outbreaks and flash floods in recent American history, and until now, nobody has ever observed one directly with the kind of detailed instruments this new mission is bringing. The mission carries an official name, the North American Upstream Feature Resolving Antropopause Uncertainty Reconnaissance Experiment, and researchers describe it as a genuinely unprecedented opportunity to close a gap in atmospheric science that's persisted for years. Stick around, because understanding what happens when these two jets collide explains a surprising amount about why certain storms turn catastrophic almost without warning. Let's be clear about what's actually new here and what isn't. Scientists have known jet superposition happens for a while now, and they've retroactively linked it to specific historic disasters after the fact using weather model data. So this isn't a case of discovering a brand new atmospheric phenomenon nobody knew existed. What's genuinely unprecedented is the direct observation piece. Researchers have never flown dedicated instruments into an active superposition event to measure its internal structure in real time, which means a lot of what scientists currently believe about how these events work is still built on inference rather than direct measurement. Here's the mechanism so the whole picture makes sense. The polar jet stream and the subtropical jet stream are both fast-moving rivers of wind high in the atmosphere, but they normally operate independently at different altitudes and different latitudes, each driven by a different temperature contrast in the atmosphere below them. The polar jet sits farther north and responds to the temperature difference between polar and mid-latitude air. The subtropical jet sits farther south, closer to about 30 degrees latitude, and responds to a completely different temperature gradient tied to the tropics. Under normal conditions, these two systems stay separated enough that they don't meaningfully interact. Occasionally, though, a specific sequence of events pulls them together. Organized clusters of tropical thunderstorms over places like Indonesia can push the subtropical jet stream north, and if the polar jet happens to dip south at the same time, the two currents can merge or even superpose, meaning they stack vertically in the same location rather than simply crossing paths. When that happens, the wind shear in that narrow zone becomes extraordinarily intense, since you're now combining the energy and instability of two entirely separate atmospheric systems into one concentrated column of air. The distinction between a simple merger and a true superposition matters more than it might sound like at first. A merger happens when the two jets cross paths or run parallel to each other at a distance, which still increases wind shear somewhat, but in a more diffuse way. A true superposition means the two jets occupy nearly the same vertical column of atmosphere at the same time, concentrating the combined energy into an unusually narrow and unusually intense band, which is the specific configuration researchers believe is responsible for the most explosive, severe weather outcomes. Now let's stack the evidence showing why this matters, layer by layer. The first clear case researchers connected to this mechanism traces back to 2010 and 2011, when a University of Wisconsin-Madison team, led by atmospheric scientist Jonathan Martin, identified a jet coupling event linked to both a historic deluge in western Tennessee and the devastating tornado outbreak that tore through Alabama in April of 2011, an outbreak that killed more than 300 people and remains one of the largest on record since the legendary 1974 super outbreak. Martin's research traced the trigger for that coupling all the way back to organized thunderstorm activity over Indonesia, roughly 9,000 miles from where the storms actually touched down, with the disturbance propagating through the atmosphere over a period of 7 to 10 days before manifesting as extreme weather in the American midsection. What made that finding so striking to the broader meteorological community at the time was the sheer distance involved. A cluster of ordinary tropical thunderstorms on the other side of the planet, thousands of miles from the American South, was quietly setting off a chain reaction through the upper atmosphere that would eventually help produce one of the deadliest tornado outbreaks in modern American history. That kind of long-distance atmospheric connection, sometimes called a teleconnection, is exactly the type of relationship researchers are still working to map more precisely today. Layer 2 comes from broader climatological research examining jet streak types across 3 decades of tornado outbreak data in both Tornado Alley and the Southeast's tornado corridor. That research found that outbreaks involving merged or superposed JET configurations weren't just common, they were disproportionately represented among the most intense tornado outbreaks in the historical record, suggesting this specific atmospheric setup isn't a minor factor, but one of the primary ingredients behind the most dangerous events. Researchers behind that work specifically classified jet streak types across the dataset as either subtropical, polar, merged, superposed, or unidentified. And the pattern that emerged showed a clear relationship between the more intensely coupled configurations and the outbreaks that produced the highest tornado counts and the most significant damage. Layer 3 brings the story into the present. NASA's upcoming mission, officially called the North American Upstream Feature Resolving and Tropopause Uncertainty Reconnaissance Experiment, or NURTURE, is specifically designed around this exact gap in scientific knowledge. The mission will fly through the winters of 2026 and 2027, and researchers presenting on the project have described it as an opportunity to observe the internal properties of jet superposition events in unprecedented detail for the first time, using direct in-situ measurements, rather than relying entirely on reanalysis models built after the fact. Layer 4 adds a related and genuinely strange piece of context from a completely different corner of Earth's climate system. Separate satellite monitoring has recently detected colossal ocean waves, some reaching roughly 35 meters, coinciding with unusual polar jet stream shifts. Researchers studying this connection are careful to note that no single wave or storm can be blamed entirely on a warming planet, since the atmosphere has always produced chaotic extremes on its own. But they point out that the same narrowing temperature gradient between the Arctic and the tropics that's associated with a weaker, wobblier jet stream is also capable of setting up the exact wind conditions that generate unusually large ocean swells, which is why the two phenomena are increasingly being studied together rather than in isolation. It's a useful reminder that a single shift high in the atmosphere can ripple outward into systems as different as tornado formation over land and rogue wave generation across the open ocean, connections researchers are only beginning to map with real precision. Here's the genuinely speculative layer, and I want to flag it clearly as such. Martin and his colleagues have suggested that this kind of jet stream coupling, where the polar and subtropical jets interact this directly, could become more frequent as the climate continues to warm, based on how the underlying temperature gradients driving each jet are expected to shift. This remains a projection rather than an established trend, and NURTURE itself exists partly because researchers currently don't have enough direct observational data to confirm or rule out that projection with confidence. I'm including it here because it's a genuinely important open question driving the mission, not because scientists consider it settled. If breakdowns like this, the kind that explain the actual atmospheric mechanics behind the most dangerous storms rather than just the storm itself, are useful to you, like and subscribe, because this channel covers exactly this kind of overlooked science regularly. Zooming out, here's why this particular gap in scientific knowledge matters beyond pure curiosity. Severe weather forecasters already use jet stream configuration as one of their key ingredients when assessing tornado. Outbreak risk days in advance, but the precise internal dynamics of a superposition zone, how the wind shear actually behaves at different altitudes within that narrow band, remains something forecasters currently infer rather than directly observe. Better direct measurements from missions like NURTURE could meaningfully improve how far in advance forecasters can flag the specific atmospheric setups most likely to produce the most violent and hardest to predict tornado outbreaks. None of this changes how you should respond to a tornado warning today, since current watch and warning systems already account for this risk factor using the models available now. What it does mean is that the science behind those warnings is actively being refined in real time, and the improvements coming out of missions like this one could translate into meaningfully longer lead times for the public within the next several years. So here's what's actually useful for you to do with this information. If you live anywhere within Tornado Alley or the Southeast's tornado corridor, know your family's severe weather plan before storm season arrives each year, including a specific safe room and a way to receive warnings that doesn't rely solely on your phone, since power and cell service can fail during the most severe events. A weather radio with battery backup remains one of the most reliable ways to receive an alert during exactly the kind of fast-developing, high-shear event this research is focused on. Pay attention to your local National Weather Service office's Outlook discussions during active, severe weather season, not just the watches and warnings themselves, since forecasters often mention jet stream configuration and wind shear, specifically when they're concerned about an especially dangerous setup developing. Terms like jet coupling, strong wind shear, or dynamic setup in a forecast discussion are worth treating as an extra note of caution, even before a formal watch is issued. If you're in a mobile home or similarly vulnerable structure, identify your nearest sturdy shelter now, rather than during an active warning, since research consistently shows evacuation decisions made in advance save more lives than decisions made once a tornado is already on the ground. This matters even more in setups linked to jet superposition, since these events have historically produced some of the fastest developing and most intense tornado outbreaks on record. It's also worth building a small severe weather kit specific to tornado risk, separate from any general emergency supplies you might already have. A helmet or thick padding for head protection, sturdy shoes to keep near your shelter space, and a way to signal for help if you become trapped under debris are all details that specifically address tornado injury patterns rather than general disaster preparedness. Reviewing the setup once at the start of each severe weather season is only a few minutes and ensures it's actually ready if a fast developing outbreak gives you only minutes of real warning. Here's the honest summary of what this all means. Scientists have suspected for over a decade that a rare vertical stacking of the polar and subtropical jet streams drives some of the most violent tornado outbreaks and floods in American history, based on after-the fact analysis of events like the 2011 Alabama outbreak. What's never happened before is direct in-flight measurement of one of these events as it actually unfolds, which NASA's upcoming Nurture mission is specifically designed to finally provide. Whether that new data confirms Martin's hypothesis that these events could become more frequent under continued warming remains an open question. The mission itself is built to help answer, and it's exactly the kind of foundational science that could reshape severe weather forecasting within the coming years. For now, the most responsible takeaway is patience paired with preparation, since real answers from direct observation are still a season or two away from actually arriving. If clear breakdowns of the science behind the headlines are useful to you, subscribe so you don't miss the update. Once this mission actually starts flying and the first real data comes in, stay weather aware, stay curious, and I'll be back the moment there's something new worth breaking down.